chapter 27, practice questions, work solutions. So question 1A, part I is looking for the decay equation of uranium-238, so formation of uranium-239 from 238. So we've got 238, 92 uranium turning into 239, 92 uranium. If we look at the top and bottom numbers, we've got a difference of 1 and 0, okay, and that's a neutron. Similar for part 2, we're looking at when we get 239, 92 forming 239, 94 plus some mystery thing. Okay, if we look at the top and bottom numbers, we've got a difference of 0 and -2. Okay, to get -1, we're going to end up with 2, okay, 0 and -1, and that is an electron or a beta minus particle. Okay, so we're getting 2 times, beta minus particles. Question 2, part B, talking about breeder reactors and the for and against. So for is reusing nuclear waste for energy, so reusing waste for energy, and longer lifespan of nuclear fuel. Against can be used as cover, I'll explain that in a minute, for nuclear weapons creation. Okay, so you can use breeder reactors as sort of a cover, so like a pretend that you're making breeder reactors for commercial use, but actually use them for weapons. So Iran was sort of in recent history, we were worried about them potentially doing that. We can do some research on that. Second against would be requires time, money, and energy. Okay, it's not easy to do. Finally, as yet untested tech, both commercial and safety. Okay, so we don't know whether it makes more money than it takes in, so commercially, and we don't know whether it's actually safe for use. Question 2A, so talking about binding energy. So binding energy is energy required to separate nucleus into constituent, so the separate nucleons. Mass difference, okay, delta M, is change in mass from total nucleus and constituent nucleons. Okay, so it's the difference between the two. Part 3 is asking for the relationship between these. Binding energy is equal to binding energy is equal to delta M c squared, where this is velocity of light, and delta M is the mass difference, as I said before. Part B, calculate the average binding energy per nucleon in MeV per nucleon of the zinc nucleus, zinc 64. So we're looking for that delta M, which is going to be 64 times U, which is what it should be. That's the mass of the constituent nucleons, minus 63.92915 U, and that gives us a difference of 0.07085 U. U. We can use the conversion that 1 U is equivalent to 931.3 MeV. Okay, so end up with binding energy per nucleon is 0.07085 times 931.3 divided by the total number of nucleons, which is 64, and that gives us 1.03 MeV per nucleon. Part C, why would you expect it to be stable? As this is larger than other nuclei. So this binding energy per nucleon is larger than other nuclei, e.g. polonium or plutonium, any of those. Okay. 3. Describe the physical process, nuclear fission. Smaller nuclei combine to make larger nuclei. Energy released. Part 2 is fission. So this is the opposite, larger nuclei split to form daughter nuclei. Energy released. Part 3 is why is that releasing energy, and this is because the binding energy per nucleon of final nuclei in both is greater than initial. Okay, so the binding energy in fission, the binding energy of the daughter nuclei is greater, so per nucleon is greater than the original. In fusion, the binding energy of the nucleus produced is greater than the constituent nuclei that fuse together. B, energy is released in radioactive decay. Talking about how the energy is released. This is very simply looking for in joules. So again, energy is delta M C squared. So if you work out the mass difference first, that is going to be 219.96410 minus 215.95572 plus 4.00150. Let's do like 6. Okay, so this is the binding. This is the mass before. This is the mass after. All of that times U. Okay, so if we work that out and then multiply by U, which we get, sorry, 6.88 times 10 to the minus 3 U, times that by U, which is 1. This is in the formula sheet, 1.661 times 10 to the minus 27 kilograms, and we get that mass difference as 1.14 times 10 to the minus 29 kilograms. Don't clear your calculator because we're going to use that. Then the energy is this answer times c squared, so 3 times 10 to the 8 squared. Do not forget to square it. Okay, that comes out rounded to 3 significant figures as 1.03 times 10 to the minus 12 joules. 4. This starts off as not a nuclear question, but it does get there in the end. Question 4, power. So part A, talking about solar panel power, is V times I, which is 20 times 2.4, gives us 48 watts. Talking about the efficiency of the power panel, the power in is the intensity times that area, is the intensity per area times that area, so 1,400 watts times 2.5 meters, which comes out as 3,500 watts. Efficiency is P out. This is P out, by the way, sorry. P out divided by P in times 100. 48 over 3,500 times 100 comes out as 1.4%, so not particularly efficient. B. Let's talk about the backup power system, radioactive parts at B, part 1. Show that the container absorbs the energy, so the energy, total energy, is the activity times the energy of the radiation, which is 1.1, times 10 to the 14, times 5.1 MeV, which comes out as, so they want it in joules, so we then times that, times 1.6 times 10 to the minus 13 joules, okay, times 10 to the minus 13 because it's MeV. Okay, this number's in MeV, so we're only using times 10 to the minus 13 there. Comes out as 89.76 joules per second. Okay, because this is technically in seconds to the minus 1, which is equivalent to 90 joules per second, or approximately. 2. Calculate the decay constant. This is very simple. Decay constant is ln2 over t half. Okay, the only thing we need to make sure is we're putting this in seconds. So we've got 90 times the number of days in the year, which is 365.25, accounting for leap years, times the number of hours in a day, which is 24, times 60 squared, which is the number of seconds in a minute, and the number of minutes in an hour. That comes out as 2.44 times 10 to the minus 10 seconds to the minus 1. Part 3. Mass number of the isotope is 239. Calculate the mass of the isotope. So this is one of the more harder questions they can ask. And it requires, well, the first part requires A equals lambda n. Okay, the only problem is we don't know n. So we need to use the molar mass effectively to work that out. So we end up with n is Na times ms over m. Okay, where n is the number of nucleons, Na is Avogadro's number, which is in the formula book. This is the mass of the substance, and m is what's called the molar mass. Okay, you'll come across this in thermal physics, the molar mass, which is also the mass number, or to make it really confusing, A. Okay, but not A as in activity, A as in A equals 239. Okay, the number of protons and neutrons. A way to remember this, okay, the way that I remember this is as saying NAMIS, okay, never mind. So imagine one of your female teachers is asking you what you were talking about, and you'd say, nah, miss, never mind. Okay, that is Na, na, miss, ms, equals nm, never mind. Okay, that's a good way to remember it. So going back to the original part, we're going to go A equals lambda n, and we're going to use n equals Na ms over m. Combine those to get A equals lambda Na ms over m. Remember, ms is the mass of the substance. That's what we actually want. So we're going to rearrange that to get A times m over lambda times Na equals ms. Plug in the numbers in. We'll have 1.1 times 10 to the 14, which is from the question, times 239, which again is from the question, divided by 2.44. Remember, we're not using 2.44. We're going to use our answer from the previous part. So we're going to use the full number here. Okay, that's the full number we're going to use. I'm just writing this down for shorthand. Times by Avogadro's number, which again is in the formula book, 6.02 times 10 to the 23. and that will give us a mass of 179. Now, confusingly, molar masses are always in grams. Okay, that's all it is. It's always in grams. So it's not in kilograms. It's the one case we don't use kilograms. 5 is our binding energy per nucleon against mass number graph. Okay, so it talks about copying the figure and demonstrating where the most stable nucleon is. Okay, you should know that this is iron, but in case you weren't, it's the one that's going to be right at this peak here. So we'd label that S. Okay, because it's with the greatest binding energy per nucleon. So you could read this off the graph, but I'm going to use iron, which is mass number of 56. Okay, binding energy per nucleon from the graph, I read it as about 8.8 MeV. Okay, again, if this is an exam question, there'll be an order of reasonable accuracy allowed there. So again, we're going down to get one number there, which is A, going along to get binding energy there. Okay. Part 3, the total binding energy, so kind of an inverse of the question we were doing earlier, is going to be the A times binding energy per nucleon. So 56 times 8.8, which comes out as 493 MeV. Okay. B, talk about fusion reactions. Part I, wrong way around. 0.1e represents a positron. A beta plus particle, the same thing. Beta plus particle. Okay, because we've got a positive charge there, so it's a beta plus. Okay, and that represents an electron neutrino, even though they haven't put the subscript E on there, so it should strictly have that. We know it's got to be an electron neutrino because this is an electron. Okay, it needs to be the same type of neutrino. 2, charge baryon number, so this is going back to particle physics stuff. So again, we write charge, baryon number, lepton number, remembering we have lepton electron and lepton muon number. Okay, we won't need to use lepton muon because we don't have any muons, but it's good to get in that practice. So left hand side, the total charge is 1 plus 1 is equal to 2 plus 0. Okay, both sides equal the same, that's fine. Baryon number, we have 1 plus 1 equals 2, because we've got 2 baryons in the deuterium, plus 0, so that equals. Lepton electron, we have 0 plus 0 equals 0 minus 1, because this is a positron, which is an anti-electron, so that's an anti-lepton. Okay, plus 1, because we've got the muon, both sides equal 0, that's fine. 0 equals 0 for the muon number, because we don't have any muons, so that's fine. Okay, therefore that can work. 3, again using some sort of previous stuff in the course. So this is working out the wavelength from the energy. So energy equals hc over lambda. Rearrange that to get lambda equals hc over e. Putting our numbers in from the formula book, we get, I've lost my sheet, there we go, 6.63 times 10 to the minus 34 times 3 times 10 to the 8, both from the formula book. The energy, which is given us before, 0.51, times that by 1.6 times 10 to the minus 13, because we need that energy in joules. We're working out a wavelength in meters, so we need that energy in joules. Gives us a wavelength of 2.44 times 10 to the minus 12, which is 2.44 picometers. So, moving on, we've got part C. Okay, talking about why fission of a heavy nucleus is likely to release more energy, okay, than a pair of fusioning nuclei, and it's simply because number of nucleons is greater, so total binding energy is more. Okay, although the binding energy per nucleon is greater, so you get more bang for your buck with fission. With fusion. With fission, you've just got a greater mass, a greater number of nucleons, so you're going to get a total greater number. Question 6, talking about why binding energy is released in fission. Okay, so binding energy per nucleon of product is greater. And why is it hard to overcome? Why is it hard to do? Overcome Coulomb repulsion, or the electrostatic force, whichever you prefer to say. Another one, working out the mass difference here. So part 1, the mass difference. It's really, really simple, as what we've done before. So it's going to be effectively 2 lots. 2 lots of our deuterium. So that's going to be 2 lots of 2.01355 minus our tritium, so our helium nucleus, which is going to be 3.01493 plus a neutron, which is going to be 1. Okay, so that gives us a mass difference of 1.22 U, sorry, times 10 to the minus 2 U, and we can give that in kilograms, converting from U, that answer, times 1.661 times 10 to the minus 27, again, which is in the formula book. That gives our answer as 2.02 times 10 to the minus 29 kilograms. Okay, they haven't specified how they want it, but just in case, give them both. The energy released in joules, handily enough, we've worked this already out in kilograms, so we can work out the energy as delta mc squared. So we're going to use our answer from before, using the full answer from our calculator, times 10 to the 8 all squared, and that comes out as 1.82 times 10 to minus 12 joules. 7, talking about what is meant by different parts of a nuclear power reactor. So first, we're talking about thermal neutrons. These are neutrons which are slow enough to be absorbed by nuclear fuel. Okay, the reason they're called thermal is because, sorry, I'm not connecting it. EK is roughly thermal energy, so at what we call thermal speeds. Okay, so that the energy, the kinetic energy of those neutrons is about equivalent to the average energy of the sort of nuclear fuel at that temperature. So they're approximately similar energies. It's not like they've got masses of kinetic energy at that point. Induced fission. That would be fission that occurs due to external factors, e.g. most commonly neutron bombardment. Okay. 3, self-sustaining chain reaction. Just a bit self-sustaining chain reaction. Okay, so this one is further fissions are induced by prior fissions. Okay, it's a bit short because I'm running out of time here, but effectively further fissions, each subsequent fission is caused by a prior fission, so leading to continuation of fission reaction until fuel is spent. For B, talk about moderation. B part 1. The moderator slows fast neutrons to thermal speeds. The role of, also how fission is controlled is via control rods, which absorb the neutrons, e.g. made of boron, commonly made of boron. Can be made of other stuff, but boron's an example. Question 8, talking about why fuel rods that have been used are more dangerous and less radioactive. Okay, the less radioactive is the radioactive isotope has decayed away, and the reason they're more dangerous is other radioactive isotopes. Isotopes are formed. So, e.g., there's ones like plutonium is formed, which is an alpha emitter, which is quite dangerous when sort of breathed in. Okay. B, describe how they're handled. So this is high-end nuclear waste, or high level, sorry, not high-end, high level nuclear waste. So it's quite dangerous, high radioactive. So initially it's cooled in water baths or water tanks. Okay, so it's cooled down. Sealed in concrete lined metal drums, or vitrified. So that's where it's melted into glass, so sealed in glass effectively. Both of these stop radiation reaching people. The advantage of vitrification is no leaks into water. Okay, so if you're conscious of it leaking into your water supply, vitrification, which is done in some countries, is better. So you could effectively put it underwater and it wouldn't affect the water supply because it can't leave the glass. Can also be, it's then kept underground or far away from populated areas. So in the UK, so e.g. it's managed in Sellafield, okay, which is in Cumbria. And their closest neighbours are just sheep, basically. So there's not a lot of people to get affected if it does leak. And then also secured from malicious theft, e.g. for terrorism. Okay, so all this stuff is very, very secure to stop someone stealing it and doing anything dangerous with it. Done.